The last video we did was long and quite complicated. So this video, we're going to make it a bit shorter and a bit simpler. So in this video, we're going to look at a piece of code that we can use in order to test out the floating point unit. Now it doesn't test everything in it, but it gives us a flavour of how we can run a little test script. Also, we're going to look at an online tool which I've created, which will allow you to convert from decimal to float and float to decimal, and it will also allow you to do the floating point addition, subtraction, multiplication, division and our square root. So let's crack on with that now. So if you go into the ASM folder and you come down to the file that says testfpu.asm. So this is a little test script put together in order to test just the basic functions of the floating point unit. And you can see here that we're testing the addition, subtraction, multiplication, division and the square root. Now we start off by putting the values into the registers. So we put the values in using the data command, and you can see here the different formats that we can use. So we can put a number in here, hash 3.762, so that's just a normal decimal number. We can put the negative number by putting a negation in front of it. We can also put the number in terms of the hex value by using hash 0 cross. We can also put the number in terms of an exponent raised to the power of -2, and again here's an exponent here to raise to the power of 1. So there's lots of different formats in which we can actually enter in our floating point number and our numbers, and they will be interpreted as floating point numbers within the assembler. Now whenever we work through each of these, so we take the addition one first of all, we're going to add these two numbers, 3.762 and -2, and we should get 1.762 as a value. And we're going to store them in memory locations. So in this instance here, the number gets placed in res_add. So we come down to the very bottom here. You can see here we've set aside our memory locations. So the memory locations start at 0 cross B 000. So that'll be for add, and then it'll be 0, 1, 2, 3 and 4, and you can also see that we've got the actual answers that we expect to see written in our hex value here. Now I'm not going to talk through the individual pieces of code. Now they're relatively straightforward here. We're going to push the value of R1 onto the stack because presumably we want to maintain that value of R1, okay, so that is we want to be able to pop it back off whenever we're finished doing the addition. So we do the addition here, R0, f add R0, R1, it'll put the value in R1, we store that value in the memory location res_add, as in result_add, and then we pop the original value that was in R1 out of the stack and back on to into the register. And we do a similar thing for each of these, okay, and we should get these results here. So I'll take a little screen snapshot of these so that we can actually see what the values are going to be. So I'll take a little snapshot of this. Okay, so let us we'll assemble it and we'll run it and we'll just check the values out, okay. So we can go terminal, run task, assemble file, and that's the assembly successful. So let's go ahead and we will load it into our machine and we'll see it running. So we can drop into our RAM and we can open up the file. Now the file is going to be in the .mc folder and it's called test fpu .mc, so it's this one here. We can open it up, and this is the piece of code which will run through that entire bit of assembly language. So we'll close that, design user panel, simulate, tick enabled, and that's it running through. I'll just check and make sure it's running at full speed. It is. So it'll take a minute or so for it to run through and generate all of the values. But we know the value is going to be, the answer is going to be in 0B00. So that's it finished now. So let's drop in and we'll actually see whether we get the correct values. So if we drop down into the RAM, now the result is at 0B00, but remember this actually starts at 8000. Okay, although it says 0000, it's actually 8000 because the ROM takes up 32K and the RAM takes up the 32K, so they're split. Okay, so if we come up here to, it should be 3000. So 1, 2, 3000. Okay, so there is the answers here. Okay, it should be just a bit big enough for you to see. Now let's go in and we'll have a look and see what the answers should be. So the correct answers should be 3F0C, which we've got, 3C, so C366, 4C40, 539. Now it says 5, but I've got A, okay? So 593A. Now you're not going to get exact values for some of the functions. For example, this one here is 1, 2, 3, the fourth one in is going to be the division, but we're going to get it fairly close, okay, or relatively close. Now the other one here is 33D7 and we've got 33DA, okay. So the division and the square root, you see, we don't get absolutely perfect values because they're done using a method of division and square root, which is in fact actually an approximation. But we can check out these values and we can see how close the approximation is by using the very next tool, which we're going to go on to and we'll look at now. So if you go into a web browser, and I have this link here, and I will add the link down below in the resources section so that you can open this up. But if you click on that, now it might take a few seconds for it to open up. Well, that's open now. You can see here it's called Float 16 Toolkit, and along the left hand side we've got some options here. So we've got the Float 16 converter, and we've got the addition, subtraction, multiply, division and square root. So the first thing to look at is the converter. So if you want, you can put the numbers in. So for example, I can put in 2.5, I can press enter, and you can see here it's done the conversion. So the 16-bit floating point number for this here is going to be 0 cross 4100. It's got it down in the binary as well, and I've split these into the separate sign, the exponent and the mantissa, and I've got a little breakdown as to how it actually goes through and generates the solution. And it's got the type of number format, so this number is called a normal number as opposed to a subnormal number. So it's relatively straightforward, so you can also put in, say, 0 cross 4100, press return, and it does it round the other way. So it'll take this here, which is a floating point number, and it'll put it into the decimal for you here. And you can also go through each of these and you can do the addition. So you could put in our 2.5 and 2.5, press return, and the answer is going to be 5, which in our floating point land is 0 cross 4500. Now we can do the same for our subtraction, our multiplication, our division, and we can do it for our square root as well. So this is a handy and useful little tool for us to use in order to check any of the values that we want to within our floating point unit. So let's have a look at our division and square root. Now if I bring up the values here that we got, so in this instance the division, we got 593A. Okay, now the actual answer was 0 cross 5395. Okay, so the answer should be 60.66 and we got 539A. So instead of 60.66, we're getting 60.81. So it's out a bit on this particular one here. Okay, now we can test the other one, which was the division. Okay, so the division, it was 3, let's have a check and see. If I open this up, the square root. So the square root was 33D7. So we put in our 0 cross 33D7. It should be 0.2450, but we got 33DA. So this is a 33DA. So 0.245 and 0.2454. Okay, so it's a lot closer in this one. So it gives us a tool in order that we can use in order to check the results. So this video has given you a flavour of how to run some code to test the floating point unit, and also once it's been tested to take the values and check and see how accurate they are. Now you'll notice when I mentioned the division and square root, we've generated those using the fast inverse square root algorithm. So it is an approximating algorithm, so we don't get exact values. But the reason why I decided to go ahead and use that particular method is that it was just a much more interesting algorithm, I thought, for us to build and test and to check and see how it worked. Also, it's an algorithm that allows us to do the division and the square root purely combinatorially. Okay, that is, we don't need to clock it through. So if we had used an exact method, then we would have had to have used many potentially clock pulses in order to generate the division and square root. So it makes it a little bit quicker, but it's a little bit less accurate. But it's also, in my opinion, a bit more interesting. So that's all for this video. Thank you for listening. I'll get you on the next video. Goodbye.